Hi everyone. Today we're going to start on 3.3 where we're going to talk about linear functions again. So what is there to talk about in linear functions? So we call from 3.1 we define a linear functions f that go from Rn to Rm to be this as any function that satisfy the property f of a vector x plus b vector y is equal to a f of vector x plus b f of vector y. So remember, the idea of a linear function is that it works perfectly with linear combination of vectors, where when you have to plug in a linear combination of vectors into function f, you find out that you can actually instead perform the function of the individual vector, then form the same linear combination. So what we're going to talk about in 3.3. So now what we're going to try to do is the following. Now we will try to define linear function using other vector spaces. Such as the matrix space, the polynomial space, or the continuous function space. So that's the end goal here, is to try to define linear function, not just on vectors from Rn to Rm, but instead try to define it on other objects, such as matrices, such as polynomials, such as continuous function. Now, but of course, the general idea is remain the same. The general idea is that we're going to try to kind of in some way make those vector spaces or their subspaces to behave similar to Rn and Rm, so therefore allow us to actually use the already established linear functions property to actually work on those. Now, however, one thing I do want to point out is the following notes. For function f, for linear function f that map from Rn to Rm, it can always be represented in matrix form. So that can always be done if we go from Rn to Rm. As a matter of fact, if your matrix, your function go from Rn to Rm, then you actually will form by a matrix M by N. Okay. Now, however, linear functions with other vector spaces cannot always, so meaning some of them can, but not all of them, cannot always be represented in matrix form. Now, of course, if it can be represented in matrix form, it will make our life a lot easier. But there are some that won't be able to do that, and unfortunately for those that we cannot do it, we just have to live with it and try to figure something else out. So some terminology that I want to define for you, and as a matter of fact, it's the same terminology that you probably remember learning last year in multivariable calculus. If we define a linear function f between, let's say, two different vector spaces. Then, okay, well, maybe I write something like this. Such as in this case, f go from V to W. And if these two vector spaces are significantly different than each other, then we'll sometimes refer to it. We often refer to this linear function as a transformation. Especially if the vector space V and W are viewed as something kind of completely different. Okay, then we will refer to this as a transformation, which makes sense because the word transformation basically means change. So therefore, in this case, if you define a function that kind of changes the domain and the range, then it will make sense to call it a transformation. Now, what if it doesn't? If the linear function doesn't really define between two different vector spaces, but maybe between one vector space, or maybe a vector space with some of its very similar subspaces, then if that's the case, then if we define a linear function f within a vector space, or sometime with its subspaces, such as f that map from V to V. So that would be one function that works within a single vector space, where everything that you do with this function would just simply result in another element or another object within the same vector space. Then if we do that, then we often refer to these type of function as an operator. Or basically meaning an operation, pretty much. So we're basically doing an operation, and because whenever we do an operation, we basically just combine element of the same group together to form another element within the group for the most part. So therefore, when we do that with a linear function between a vector space and itself, then we can simply call it an operator, because we're basically operating on element within one vector space, so they go back into the same vector space. So because of that, now a very simple example would be this example right here. Imagine the following. Imagine I define this. I'm going to go ahead and say let's P be the polynomial space. So therefore, that means that P represent all polynomials of any degrees. So if that's the case, then I can now define an operator in it. I'm going to define D to be the what we call differential operator. Now, this is a very important operator that you kind of need to know. Differential operator. So what does the differential operator do? Define D to be the differential operator such that this is true, such that when I apply the differential operator on a function, a polynomial p of x, it will result in the derivative of p of x. Now here's something interesting to think about. In this scenario here, our differential operator, in this example of the function, this basically define our differential operator in the vector space P. And if I take a derivative of a polynomial function, what is the resulting function look like? Well, guess what? The resulting function is also a polynomial. Now, granted, some of you might be thinking, wait, but the degree is 1 degree lower. And you are correct. So you could think of the differential operator as a differential operator that go from p sub n to p sub n minus 1. And that will work, but notice that p sub n minus 1 and p, even though they're two different vector spaces, but one is a subspace of the other. And the object involved are actually very similar to almost identical. So therefore, in this scenario right here, it's probably easier or more appropriate to define it as an operator than a transformation. Okay, and granted, it does change the dimension a little bit, but in all honesty, it still simply gives you a polynomial. So therefore, it's probably more appropriate to call it an operator than a transformation. So that's the terminology we'll be using. As a matter of fact, differential operator is extremely important. You should definitely know what it is. So show you how this works with a differential operator. So example, suppose I take the derivative of a polynomial function, and guess what it come out? So there you go. So if I take the derivative of a polynomial function x to the third plus 3x plus 1, it's going to give me the derivative of the polynomial function, which in itself is another polynomial function. Now, I did call this differential operator this thing a differential operator, which basically meaning that I'm kind of claiming that this is also linear. So let's find out if it's linear. So how do I show that it's linear? Well, to show that linear, I have to show that it satisfies the property that we set for in 3.1, except that we are not talking about vectors in Rn, but now talking about polynomial function. So how does it work? Well, show you how it works. So to show that this is a function, what I'm going to do is this. I'm going to given, let's say we're given two polynomial in P. We don't care what degrees they are, but I'm going to go and call this P of x and Q of x. The question that I want to find out is, if I take the derivative of a linear combination of P and Q, does that mean the same thing as if I take the derivative of P and Q first, then form the same linear combination? Well, let's find out. So basically what I have to show is this. I have to show that if I take the derivative of some constant a times P of x plus some constant b times Q of x, that should equal to a times the derivative operator of P of x plus b times the differential operator of Q of x. That's what I need to show. So how do I show this? Well, simple, just like what we did before. What I'm going to do is I'm going to show the left-hand side and the right-hand side. I'm going to try to show that they both give me the same thing. So let's try the left-hand side. So suppose I'm going to try to take the derivative of this thing. So how does it work? Well, so that basically just means I'm taking the derivative, I'm differentiating a P of x plus b Q of x. Based on what we know about taking the derivative of a function, I can definitely separate this derivative into two. And then we also know that I can actually pull out the constant from our differentiation. And then if I take the derivative of P of x, I just get P prime of x. And if I take the derivative of Q of x, I get Q prime of x. So that's what I get to at the end if I do the left-hand side. Guess what happened to the right-hand side? If I do take the right-hand side, then that just means A, take the derivative of P of X plus B times the derivative of Q of X. And guess what? That just come out to be this. Which I can see that they're both the same thing because they both equal to the same exact expression at the end. There you go. And so therefore, we just show that this differential operator D is linear. Now, however, one of the important property about linear function, or as a matter of fact, any function in general, but more so for linear function, is that is this function one-to-one. The reason why one-to-one is important is because it directly relating to whether this function has an inverse or not. Remember, if a linear function is not one-to-one, it cannot have an inverse. So in this case, is D one-to-one? Note, D is not one-to-one. As a matter of fact, a lot of you already know this. D is not one-to-one because if I take the derivative, if I differential operator on the polynomial function x squared, I'll get 2x, which is the same as if I take the differential operator and apply on 2x squared plus 1. Both of these functions give me the same exact output, which is 2x. Okay, but they are not the same function to begin with. So therefore, D is not one-to-one. Now, because the concept of one-to-one is very important, it's probably a good idea to know how to define a linear function to be one-to-one. Now, of course, we already have a definition before. We have a definition in 3.1 that tells us whether a linear function is one-to-one or not. So why do we now need a second definition? Well, because if you go back to your notes on 3.1 and look at your notes, the theorem that states whether a linear function is one-to-one requires us to look at the matrix of the function and show that the matrix is the columns of the matrix are linearly independent. The problem is our differential operator right here, this linear function, does not have a matrix representation at all. Okay? We don't have a matrix representation. So I cannot really show you how to determine is one-to-one using what we have learned in 3.1. So does that mean we're stuck? Well, obviously not. It just requires us to think of a different way to define linear one-to-one properly. So here is the theorem that tells us what happened. Theorem 3.3.3, which states the following: a linear function f is one-to-one if and only if this is true. If only if vector x equal to 0 vector is the only solution to the equation f of vector x is equal to 0 vector. Now, this statement requires some explanation before I can show you. So number one, this statement actually works with 3.1 definition, because if you think about it, if a matrix has all its columns to be linear independent and is a square matrix, then that would mean that you could basically set equal to 0 and then reduce the matrix down to the identity matrix, which basically tells you that every variable would equal to 0, which is basically what this statement is saying. It's telling you that vector x is equal to 0. Because if you think about it, you remember learning it from last year. Okay, you remember learning from last year. If you have a system that's equal to 0, and that system has a coefficient matrix that has an inverse, then that would mean that you have only one solution. That solution is a 0 vector. So this theorem basically plays on that concept. Now, however, with that being said, I do want to point out the following. See, this theorem seems to suggest that vector x is a vectors in Rn, and the 0 vector is the 0 vector that we define to be like all 0. However, it's not technically true. See, this statement actually allows us to also define things that happen in other vector spaces. So meaning in this case, a vector x could actually be a matrix, could be a polynomial, could be a continuous function, could be any of those stuff. And then the 0 vector simply referred to as the 0 element within the vector space that we define. So, for example, let's say we define D to go from P to P. So I'm going to define a differential operator that only work on polynomial function and always result in giving us another polynomial function. Now think, what is the 0 element in P? What's the 0 vector in P? Well, the 0 vector in P would be this. The 0 vector in P is the function that I like to call z of x that equal to 0. Okay? So therefore, what does that imply is the following. In order for D to be 1 to 1, it implies the following. So in order for D to be 1 to 1, it implies that if I take the derivative of the 0 function, I get the 0 function. Okay? And I cannot achieve that by any other function at all. And no other polynomial p of x that would satisfy That's basically what the 1-to-1 need to be for D. But we know that's not true. Well, of course, for once, we already told you that D is not 1-to-1, so you know that's not true. But it shouldn't be too hard to figure out in counterexample. As a matter of fact, okay, to be fair, this is true. D of the function 0 will give you 0. That is true. Remember, that's what z of x is 0 function. But it is also true that if p of x is equal to some constant k, then d of p of x, which is equal to d of just some constant k, would also equal to 0. So therefore, meaning in this case, not only our 0 element, z of x, which equal to 0, or the 0, would satisfy the equation that when I put it through the differential operator, I get 0. But as a matter of fact, any constant polynomial would also do that. And so therefore, it shows that D is not 1-to-1. So we show that z of x equal to 0 is not the only solution. To the equation d of In this case, I'm going to call p of x equal to 0 of x, which is equal to 0. So important to notice that even though the theorem use vector x and vector 0, but they are actually referred to as the element within your vector space and the 0 element within your vector space. So keep that in mind. All right, and so next thing I want to show you is this. So hopefully I have enough time to show you this. So imagine the following. Okay, let's say we have this. Let's define the following. Let's say I'm going to define C parenthesis 1 of x be the set of continuous function with continuous first derivative. With the domain x. Then notice what happened if I apply my differential operator to this object. So think about it is that if I apply my differential operator to C1 of x, what should the outcome be? So tell me to pause the video and think about it, okay? And then I'll go give you the answer. So hopefully you have time to think about it. So what would the range be? So here this is also always gets confused because the range in this case is actually going to be this. Why? Because think about it, if you take a function that have a continuous first derivative and you take the derivative of that, then what you get would be a continuous function because C parenthesis 1 already established that any first derivative of within this set are continuous. The reason why I often get confused is that, but wait a minute. Isn't C parenthesis 1 the first continuous first derivative space a subspace of continuous function? And you are correct. And so then how does that work with a smaller vector space in the domain mapped into a larger vector space? Does that kind of not make sense? The answer is no, it makes perfect sense. The reason why it makes perfect sense is because, remember, in here, the continuous function space is a range. But the image from this differential operator could be smaller and reside within C. So therefore, you can think of it as the following. Is that you're basically taking a smaller group of function from C, which is the C parenthesis 1, the continuous first derivative function space. And then when you plug it through a derivative, you actually find a continuous function from that. And so therefore, it maps into a similarly smaller subset of the continuous function. So still often get confused. And most likely the reason why they often get confused is that they're thinking like, shouldn't it be reversed? If you take the derivative of a continuous function, you get the first continuous, but that doesn't make sense because if you take a derivative of a continuous function, then the derivative can be discontinuous. We don't know that. We don't know that it's continuous or not continuous when you take the derivative of some function. Some function that we know have a continuous derivative, like let's say x squared, but some continuous function that we know has and discontinuous first derivative, like absolute value of x. So therefore, it cannot go from differential operator on continuous function to the first continuous function space. That doesn't make sense. But if I choose only to take the derivative of functions that has a continuous first derivative, which is what we have right now, then the result would have to be a continuous function because that continuous function represents the continuous first derivative. So it's it's sometimes confusing, but if you take a minute to think about it, it will make sense the way that it is. And if it still doesn't make sense to you, we can talk about it during class. So now it's about 29 minutes in the video, almost 30 minutes. So I think I will stop right here and talk about the next example on tomorrow's video. All right, talk to you guys soon. Bye.